Question 7, the first part is actually just a fairly straightforward titration calculation, but with a slight twist in the tail, which is that you've got to give the concentration in these unfamiliar units of milligrams per dm cubed instead of moles per dm cubed. But that's only going to be 1 mark at the end, which we'll worry about in a minute. The main part is fairly standard stuff. But there's a lot of information there, so you've got to make sure you read it carefully. And the starting point always in a titration is you've got to identify the substance whose concentration you know and whose volume you know, so that you can get your number of moles of that substance to start with. So we've got moles equals concentration times volume in dm cubed, and the substance we can do that for is thiosulfate, because you can see in the very last line of the information you're given, 24.6 cm cubed is the volume, 0.001 moles per dm cubed is the concentration. Okay, so that's 0.00100 times 24.6 cm cubed, remember, has got to be divided by 1,000, so 0.0246, which is 2.46 times 10 to the minus 5 moles of thiosulfate in the titration. That's the first step. Now we've got to start working back to relate that ultimately to the moles of oxygen, which is what we're interested in. And you can see that that's several reactions away, because there were a series of 3 reactions occurring one after another. So we work back 1 step at a time. And the first thing we can do is relate the moles of thiosulfate to the moles of iodine, which is the third of those equations. So we get moles of iodine, and you can see from the equation is just a half of the moles of thiosulfate, which is 1.23 times 10 to the minus 5 moles. Okay, because every 2 moles of thiosulfate react with just 1 mole of iodine, so we've halved to get the moles of iodine. Now we can work back to the next stage, because if you look at the reaction above, we can relate moles of iodine to moles of MnOH3. And you can see that this time we have to double the moles of iodine to get the moles of MnOH3. We're not worrying about the moles of I- because that was in excess. It told us that. So we can say moles of MnOH3 is 2 times the moles of iodine. So we've actually just reversed what we did in the first step. We took our starting number, we halved it, now we're doubling it again. And so we get back to 2.46 times 10 to the minus 5 moles, this time of that manganese compound. Now we come to the equation at the top, and now finally we are going to get back to oxygen. And you can see that we've got to take 1/4 of the moles of MnOH3 to get back to the moles of O2. Okay, because each mole of O2 gives 4 moles of this stuff. So we get moles of O2 is 1/4 times the moles of MnOH3. And if you take 1/4 of that number, you get 6.15 times 10 to the minus 6 moles of O2. Okay, now you've got a choice at this point. You could go on and convert that into a concentration in moles per dm cubed, and then convert that at the end into the alternative unit of milligrams per dm cubed. Or you could turn that number of moles into a mass now and put that in milligrams, and then simply divide by the number of dm cubed. So we're going to do it that way, but it doesn't matter if you've done it the other way around. Okay, so we're going to say, okay, that's the number of moles of oxygen. We've got to turn that into a mass. So we get mass of O2 is moles times mR, which is 6.15 times 10 to the minus 6 times 32.0 is the mR of oxygen. Remember, it's O2, not just O. And that gives us 1.968 times 10 to the minus 4 grams of oxygen. But we want milligrams, and you have to know that a milligram is 1,000th of a gram. Just like a millimetre is 1,000th of a metre. So to turn that into milligrams, we've got to multiply by 1,000. And if we multiply that number, we get 1.968 times 10 to the minus 1 grams, which is 0.1968 milligrams of O2. And now we're almost there, because what we want is the concentration in milligrams per dm cubed. In other words, we just divide that number of milligrams by the number of dm cubed. So we can get that the concentration in milligrams per dm cubed is going to be equal to, instead of moles over volume, it's this time going to be mass in milligrams divided by volume in dm cubed, which is 0.1968 divided by, well, it's 25 cm cubed was the volume of water that was sampled, but again that's got to be divided by 1,000. So put it in dm cubed, so divide by 0.025, and that gives us 7.87 milligrams per dm cubed is the answer. Okay, now the next bit, it says comment on whether there's enough dissolved oxygen for fish to survive. So you've just got to read the waffle here, and it says that so long as the dissolved oxygen concentration is above 5 milligrams per dm cubed, the fish should be able to survive, and it is above 5, it's 7.87, so the answer is yes, there is enough dissolved oxygen. But again, put in the explanation. You wouldn't get a mark for just saying yes. You've got to say, because the number we've calculated is bigger than 5, therefore yes, there is enough oxygen. And then we come to this issue that you have to be careful with lots of these analysis methods, because they can be messed up by other things that are dissolved in the solution. And this is a nice illustration of that. So it tells you that if you have NO2 minus ions in the solution, they interfere with the reaction because they also react with the iodide ions that we needed in this method to produce extra iodine. And it says that when that happens, you produce a colourless gas with an MR of 30. So what you have to think is, well, what could that gas be? And if you look at the elements that are involved, you've got nitrogen and oxygen from the NO2 minus, and of course you've got iodine. And out of those you've got to get something with an MR of 30. And it obviously can't be the iodine, because the MR of the AR of iodine is much too high, so that drops out of the picture. So you just got to think, well, what gas could you make out of nitrogen, which has an AR of 14, and oxygen, which has an AR of 16? And it's not too hard to realise that if you add those two numbers up, you actually get 30, so the gas is NO. Okay, because 14 plus 16 gives us 30, which is the number we want. Okay, so that's one of the products of the reaction, and it asks us then to try and put a whole equation together for what happens when NO2 minus reacts with iodide. So let's see if we can do that using the information we've got to hand. So we've got NO2 minus, and we've got I minus, and we know that the products include NO and iodine, and it also tells us in the question that OH minus ions are also produced. So we've got OH minus like that. So what can we do with that? Well, the first thing is that we've got one nitrogen there, so one nitrogen there, so let's keep those numbers the same, and that means we've got an oxygen left over. And since OH minus is produced, that will take care of the oxygen. So those two things balance, but we've got to bring a hydrogen in to make that OH minus. So, usual thing when we're balancing equations, we could bring it in the form of H plus like that, and that would balance up to give us our OH minus there. The I minus, we've got to get the right number of I minuses to get the charges to balance. So you can see at the moment we've got just one minus on the right hand side. Iodine is neutral, so we don't have to worry about that. On this side, if we leave it the way it is at the moment, the charges do indeed add up to 1 minus, so that looks fine, but we've got to put a half I2 there to balance up the number of iodines in that equation. And that balances because we've got 1 nitrogen on each side, 2 oxygens on each side, 1 iodine on each side and 1 hydrogen, and the charges 2 minus and 1 plus adds up to 1 minus on that side and 1 minus on that side. So that would do. It's a slightly strange equation because you've got H plus on one side, so an acidic solution reacting to produce an alkaline solution. It tends not to work like that. It tends to be that if you've got H plus on one side, you get water on the other side, or in this case we were told we had OH minus on this side, so we would have water on that side. So a slightly better version of that equation would be NO2 minus plus I minus plus H2O instead of the H plus will give us NO plus a half I2 plus 2 OH minus. And that's just an alternative version of the equation, which is actually more realistic because now we've got a neutral solution becoming alkaline rather than an acidic solution becoming alkaline. But you'd get the marks for either of those. And that's the end of the paper.